Yes, we are set recording, about to start. Maybe people are going to jump in soon. Now, today we're going to talk about this a little bit of column design, but not in depth. If you see this course, what was supposed to be, let's imagine that you had the chance of taking it from the beginning, kind of the whole semester, not this half semester thing we're doing. So it would be kind of an opening for what you're about to see in the next semester. I think you get to see design of concrete structure, design of steel structure, and design of wooden structure, timber structure. Yeah. So they relate to one specific standard, at least in Europe. And you go a little bit more in detail about, okay, how this really is going. So if I want to calculate reinforced concrete columns, how should I do it? What is exactly what goes inside? Without going to the deepness of what a civil engineer would do and full throttle, no. So you would have a good understanding of the concepts that go behind it, the physics, what is important to take into account, what should you be paying attention to as engineers, and you have it there. This course would be kind of the introduction to these forces and everything. By the way, already the assignment is supposed to be, you're supposed to be delivered it, meaning that I will start reviewing them, checking them. Hopefully you have some important, well, not important, but nice comments there. By the way, Vishal, we're looking at your camera. It's okay for me if you want to show off yourself. And but then that was supposed to be kind of what's the standard 1990 says, then standard 1991 one and stuff. But let's talk about concept here. So we have seen about the whole structure. We saw about a little bit of the beams last week, and then let's see the whole thing that's supporting everything. And then we have the columns, and columns have a very interesting story to tell on how the design process of columns started. And this is this is really 400 years ago, or well, 200, 300 years ago. And one of the things that said, well, columns fail, like you see here in this screen, which is the pen, vanishing pen, yeah, like you see here. So this is a circular member column that if we were talking about a beam, we were talking about bend, so it deformed like bending. But when you take the beam and put it the longitudinal axis in this direction, vertical, so we call it a column. And then we don't say that it bent. What's the past participle of the verb bend? Bent, and follow bent. But we say that it buckled. It buckled. And they noticed something interesting, that if the same element, the beam, I put a load on the beam deforms. But if I put it the same beam vertically and I put an axial load here, the beam buckles, but kind of it's going to deform more or less the same. But the reasons why it deforms were different. Well, the motive why it bent was different. In the beam, what happened was, yeah, you have your beam here, and then you have certain forces applied to it, and then you have the simply supported beam, one beam we love to make exercises with, and then you have, yeah, that's fine. It has arrows, okay. So you have the deformation, something like this. In columns, the deformation is because the effect of the load pushing in that section down and creates a deformation. But on columns, yeah, the deformation is caused by the force applied to it, but not in the same way, not in the same fashion. For example, if I have here a column attached to the ground and we apply the force here, so something else is going to happen. In bending, as soon as, let's put it in this way, as soon as you release the force, kind of the deformation, so deformation is equivalent to the force applied to it, and that's it. Let's call it that something. But in columns, the force that creates that deformation is going to create even more deformation because of the deformation already existing. And we're going to see why. And so they say, well, columns might fail because they deform too much. They buckled, like this one here. And so if they buckled, so that's not good. Or like in the reinforced cement concrete, reinforced concrete column, it just crashes and then it fails. Although to crush concrete is something has to be, but there's something else here. But let's call it crushing. Yeah. So people started considering, so okay, how can we deal this wrong with the failure of columns? So imagine, hundreds of years ago, people building beautiful buildings and then the columns failing. So how should we start dealing with this? So well, okay. So we know that columns might fail by buckle or by crushing. Crushing is where it just destroys the section. So okay, let's make some considerations. The first one they're going to make is that they fail because the column is not straight or uniform. You see? So if the load is like, again, let's draw it. I believe we can have a nice figure. If this is a column, and then you have the floor here attached to it, it might be that the axial force applied to it was not that straight. Can I move this? I think I can move it. Can I? Oh, I cannot rotate it. Follow me. So it's like it is not straight, or that the shape of the column, when they were building things, was something like this. Exaggerating, yeah? So it was not a straight, beautiful straight line. So then there is an crookedness, meaning that it's already bent a little bit, deformed a little bit. There is another thing that the load was not applied eccentrically, or is applied eccentrically. Anoop, we're seeing you, your camera. Be careful. I mean, I don't care, but sometimes it just fires up out of nothing. So the load is applied centrically. An eccentrically applied load means that the load is, instead of being at the centroid of the member, centroidal axis, or aligned with the centroidal axis of the member, then what happens is that the load is like this, kind of in one end, like this. Then there are flaws in the material. Say, well, no, the material is not completely homogeneous, and it is not following completely the material law that it should be followed. Because when we talk about steel, we like to talk about Hooke's law. The guy who said that Hooke's constant and everything. The modulus of elasticity. We have seen this, but for the type of materials like glass, timber, so it's a bit different behavior. Sorry. So they said, well, there are some flaws, and well, 6 is very related to number 3. Yeah, column is not vertical, or it's inclined, or something happened. It's very related to point number 3. So that could happen. Then I want you to take home the core concepts of that. When you see a column and think about the column design, they say, well, I don't remember the formulas for column design, or I don't need to know the formulas, but I don't know what is important in column design, or how a column should be. And now, with what I'm telling you here, you already know more than many people know, that the column has to be straight, that it's not deformed already. So come on, as engineers, if you're going to you're going to see a column, you're going to use a material profile as a column, and it's already deformed. So no, don't use it, because that's going to destroy everything that this is built upon. So or there are inconsistencies in the material, let's say homogeneity inside of the member, then that's problem. So what happens about the material when you get or you buy profiles of steels from sorry from dubious vendors, meaning they don't follow quality control. The additive to manufacture the steel are not controlled by anyone. The processes are not controlled. Yeah, they produce a steel, but not the steel you need, with the properties you need. Remember that that's a spectrum. And then how the forces are applied on the column. So then you already know. Yeah, with this you can go home and say, well, I know something about columns. But then this guy Euler, he said, well, what I mentioned, columns, yeah, they deform, they buckle, but not because of what we think, because the buckling problem, buckling is, what the column deform, how the column deforms, happens It's because of a matter of equilibrium, not of a matter of force application, because the same force, the same force applied to the column at the centroidal axis, if you move it somewhere to the left or to the right, then it can be disastrous. Even a smaller, if you make a calculation and you say, the maximum axial load that this column can resist is this much, with half of that, if you put it in the wrong position, it fails. So they were realizing this. How is it possible that columns with with axial forces of smaller value still fail? So well, because this is not a problem of the magnitude of the force, but it is a problem of the point of application of the force. Hence, there's a problem with equilibrium of it. So they subdivided the cases into three parts. So, well, there is a stable case, neutral case, and unstable case. And this kind of depiction of it is very nice. What is it? Stable, neutral, unstable. It's like, having a small sphere, a ball on a concave, let's say, surface. So you drop the ball, and the ball is going to just, it's going to oscillate, until it reaches the equilibrium here. And not, if you don't put any force, that's going to stay there. Neutral means that that's going to be okay. This sphere is not going to go anywhere. But as soon as you put a small force here, that's going to go. It's going to move to the right, to the left, or depending on where the force is pushing. Unstable means that, man, that's going to just fall down with just a small hint of a push there. So there are three columns, and what does it mean in terms of force magnitude applied at the centroidal axis, the center? So if the force applied is less than something that they call the crippling load, the time you can call it buckling load, crippling load, or critical load, they are synonymous. So if it's way small, then you are considered you have a stable equilibrium, so that column is not going to fail. Then you have neutral condition, where this is hard to get because to calculate exactly these forces are very difficult, but we have an appreciation of the magnitude, that if the load applied equals to the crippling load, then you are like, if you blow on it, it would just not fall. But I'm just exaggerating, but that's the meaning of neutral. But then unstable means that if you have the load applied is way larger than the crippling load, that's going to fail. You see, it's not that, well, it's not that the section is going to compress. It is that because of the geometrical considerations, so size and shape of the section and the length of the column, that can fail. Even though the load is perfectly applied to the centroidal axis, like in this case, that's going to fail by buckling. So that's when the things of the Euler theory of buckling, or Euler buckling theory. Forgive me if I don't pronounce it Euler, because German would be pronounced Euler buckling theory. Just bear with me. I'm going to call it Euler. So for steel columns, what they did to study this, well, let's study so how we develop the mathematical equations to deal with columns. Basically, what they did was to revert the failure conditions we talked before. They said, well, columns are straight, perfect. The section is uniform, meaning that this is for steel columns, meaning that there's no discrepancies in the section. Material perfectly obeys Hooke's law, meaning that there are no flaws, no stuff inside of it. And this is something key. Length is very large compared with its lateral dimension, meaning that a column, to be a column, the length, this friend here, has to be larger, way larger than this side here. And then if you're a good engineer, you would ask, how much? How much longer? How much the difference? Well, we're going to see that in one specific parameter that columns use. Then axial stresses are very small compared to bending stresses, and self-weight is ignored. Yeah. Let me fix this at this moment. Self-weight. There it is. I just wanted to put this dot here. That's it. But when we talk about concrete, so the concrete behavior is totally different. So what they did was, so Euler didn't work with propose anything for concrete columns, but because, well, the time. But there are derivations of Euler considerations in columns. For example, that plane sections remain plane, meaning when you compress, remember what we saw in torsion, that when that deforms, the plane sections, these ones here, become remain plane. For example, if you have sections like this, when this is deforming, so the deformation, those sections are plane, so meaning they don't deform. They gave consideration about the slippage between, the bonding between the concrete and the steel is as in steel concrete, the rebars and everything. So they say we know that concrete is a bad player against tensile stresses, doesn't like it. Then axial law is concentric, which refers also to Euler. And then short columns fail by crushing. And then if you're a good engineer, you say, well, what are short columns? How short? And then slender colors are affected by second order effects, which are equivalent, a little bit equivalent to what Euler said. Yeah. So what about timber? Well, timber is a magnificent example that the timber material is called, what is it? Orthotropic, I think, if you can check the lectures. But meaning that depending on the direction you see the member, material properties are going to be one. For example, if you look at the longitudinal direction, then you have a set of material properties. If you look laterally, there's another set of material properties, and so on. So that's a discussion. Let's leave it. So when you see design of timber wooden structure, so it's going to be more evident there. Then what those guys did was, I have some figures here that we're going to take a look at. They created a term called slenderness. Yeah, slenderness is here, this one here, that relates the length of the beam with something called K, which is within the radius of gyration. I'm going to explain physically what does it mean. It's not a complex concept. So first, they said that if the relation between the length and the radius of gyration is less than 32, then we're talking about steel columns, we're talking about short column. And if we're talking about short column, most probably this is going to fail by crushing, which means that, you remember the normal stresses we saw, sigma equals to P divided by A. So this has to be smaller than the critical or the strength of the material. So this is crushing, plain and simple. That the stress, normal stress generated by the force is less than the strength that the material can support. Plain and simple. What else? That if it's between 32 and 120, then we're talking about, this is not enter. This is supposed to be like this. Yeah, this is not supposed to be like this. No. I will fix this, but I just noticing this mistake. This is supposed to be like this. What it says is that 32 less than L divided by K less than 120. Those are considered middle columns. And they can fail by a combination of crushing and buckling. Crushing is when it is crushed, destroyed. Buckling is when it deforms. But then if the relation between L and K is larger than 120, like in this case, then we're talking about a long column, and then the failure is going to be more predominantly buckling, due to buckling, which is deformation. Yeah. For the case of columns, there is not a clear definition, a kind of straight definition about slender column or anything like that. But the terms most used are stocky columns, or columns where the second order effects must be included. Yeah, and those depend on the slenderness limit, and that slenderness limit depend on the material, geometry, and some other stuff that are coded in standards. Yeah? So it's not a fixed number. It depends on cases. Now, when we talk about columns, we talk about effective length. You say, yeah, wait a second. So the columns have a length. Yeah, columns have a physical length, but that not might be the length you need to use for calculations, because depending, we're going to see it, on how you connect the column to the ground and to the upper beam, that's going to affect on how that length, physical length, is going to variate in consideration in your calculations. Yeah. So that's why we talk about effective length, and this should be L uppercase. And then the radius of gyration. What does it mean, the radius of gyration? So imagine this shape. So the radius of gyration is a measurement of equivalence. It means that if you have a defined geometry, you can always calculate a radius of gyration that tells you, okay, what about if I don't want to use with a full body, but I want to simulate that geometry as a particle? And when we talk about particles, remember the definition, there's a beautiful Euclidean definition of a particle, which means that it's a specific entity that doesn't have dimensions, but does have mass. So we love working with particles. So particles is something that you don't have a radius, length, or width, or anything. It's just something existing that only has mass. So that's the definition of a particle. And then the radius of gyration, what says, what about if I wanted to simulate that geometry using a particle? Right now, for me, it's hard to answer why they wanted to do that at the moment, but I just took it for granted. But if I wanted to simulate the mass distribution of this area around these two axes, yeah, for example, if I take this y-axis, the mass distribution of this area are going to be this one. If I take this axis, the mass distribution of this area is going to be these two ones. But if I want to simulate the mass distribution of that area as a particle, then I can always say I would have that mass distribution is going to be equivalent of me having a particle at a certain distance here from the center of the Cartesian coordinate system. And that distance is going to be called radius of gyration. No, it's not at. So whenever you see something radius of gyration and you think that's something weird, no, it's just somebody came up with the idea that I want to simulate the mass distribution of a area, of a segment with respect to a Cartesian coordinate system, but instead of using the full geometrical definition of the area, I'm using just a particle. So this particle is going to have a mass, and then the radius of gyration is the distance from the center of that Cartesian coordinate system to the mass. That's it. That's the radius of gyration. That's the definition of it. But that would help us to define how much is the slenderness, because the slenderness now is defined between the effective length and the radius of gyration. Boom, it gave us this nice concept here. And this nice concept is the one we're going to use to classify what type of columns we're working with. And depending on that, there is one row to follow or there's another row to follow, because not all columns fail the same. And for example, we have here, all I have here, this nice, this nice hand-drawn column where you have the ends, then you have the load applied here, and this is a section of the column, the beam, beautiful, everything is beautiful. But again, you can have different ways of connecting the column to the base, the column to the beam. And there are four ways that are typified or characterized in here. So both ends are pinned, one end is fixed and the other one is free, both ends are free, or one end is fixed and the other pinned. So what is a pinned end? This is a pinned end, this one here. This is a pinned end. You see there is a column here, and then there is a cylinder, a shaft that is supporting that. In my times, when when studying, we were designing these pins. Yeah, that's a academic design word. And what surprised me, something that I told you on the last lecture we had, well, 2 hours ago, that shear stresses sometimes, you can just forget about them. Look at the size of this column and look at the diameter with respect to the diameter of this shaft here. Sometimes these are massive columns still with massive weight, yet the diameter of this shaft or pin here, cylinder, is compared to that is ridiculous small. You say, why? But well, it turns out that shear stresses caused by that load are such small that you can use smaller diameter pins there and nothing is going to happen. And take into account that this design has safety factors, which means that if I get rid of the safety factors used to design the diameter of this pin here, so it will be way smaller. Look at this. When we use, there's a question from somebody, when do we use fixed pin joints? I don't have an example here, but this, depending on the case, it might be that this one, when you are on the top button, you have a fixed end, a fixed column. But I didn't find that, but depend on cases. So it might be that at the top is fixed with the rest of the structure, and you are getting that depending on the type of joint then you're going to have certain number of reactions. For example, pin joints, you're going to have, we're talking about the planar case, you're going to have 2 reactions. But when you have fixed joints, like these ones or these ones, for example, then you are going to have 3. Another question, how do we choose what kind of joints should we select? Okay, that's a nice question. I think it's more to be with the design, and also it's to be with, I'm going to show you a table in the next, let's say, pages that's going to clarify many things about this. But for example, if you are designing a water tank, you wouldn't put a pin joint here because there's not stability. So let's say that if you want to be very engineering, so the type of joint depend on guaranteeing the stability of the structure, equilibrium of the structure. Yeah. You will not put a pin joint here because this is going to fall. Yeah. So you have to put a fixed one, and this is a free end, meaning that it could do like this. There is a load here applied to the column, but this is free because it's free to move. So that depends, Samaya. That's Pen. Then one important thing about steel structures and concrete structures is that this might seem a fixed end, yeah, because if we take it from the planar case, 3 reactions, and we have it. But sometimes steel structure bolted connections are considered kind of that they allow certain rotational movement, so they do not, let's say, restrict fully any moment there. So, but that's also case to case. But pin fixed, it could be that you have this here, and then this is fixed on the top. Just an example, but that's a very good, insightful question. Then what are the and this is a table I'm going to show you. So why are the connections very important? So I didn't want to jump into the details of how supposedly, well, how Euler got from the equilibrium, stable, neutral, unstable, to the famous Euler formula for columns, which is this one. Yeah. So also that's a very nice, let's say, application. I also have a video on that, on how to derive everything and get to this. So he said, well, if you want to calculate the crippling load of the column, you need to know the modulus of elasticity, because we're talking about elastic materials, inertia, and we need to talk about the length of the column, the effective length of the column. And here's where I tell you, about. Also, this is a thing to take home as engineers. Maybe it's better like this. So the relation that exists between the physical length of the column and the effective length of the column you need to use in calculations is related to the type of ending, connection, or joints you're using. What do I mean by that? No, just get rid of it. So for example, if you have a fixed column, this is what I call the, you could use both depending on the condition, but we are in the university, so we are going to use a theoretical one. So it says that, you know what, if you are using fixed connections in your column, the deformation shape that column is going to have is going to be like this. You see, there is a part here that is going to be straight still. There's a part here that is going to be straight still, and the deformation is going to start after that. So this comes from the derivation of Newton, so the conditions. And when they did the calculation, they said, well, we can approximate that the length of the column, which is prone to deform, is going to be half of the physical length. That's why you have this 0.5, meaning that the length of the column is the physical length, but when you use fixed ends, the effective length, which is the length that is prone to deform, is going to be 0.5, that length. And this friend here is going to be your L. Now, I believe you start seeing, okay, what about if I use fixed free? If you use fixed free, this one here, then what's going to happen is that the physical length of your column, or the possible deformation that is going to exist in the physical length of your column, is approximately 1, they said. Meaning that if you have a 6-meter column, 6-meter is going to be your effective length. If it's fixed pin, it's going to be 0.7, which is the root square of 2, I think. And then if you have, well, this is free, restricted to move in the horizontal axis. But when you have truly fixed free, which means at this point, have other degrees of freedom is called, then the effective length is going to be twice the length of your physical column. And then what other we have? Pin, pin. Then we have the pin, pin, which is this one. Then it's going to be 1. What does it mean? So it means that the same column, the same dimensions, meaning the same material, the same axial load, depending on how you connect them, is going to resist more or less. If you connect them by using these fix, it's going to resist, what is it, 4 times the value of one of these pin or something like that. The pin column is the standard. Let's call it the standard. And compared to that, so fix is going to resist more. Free fix is going to resist less. So how do we choose what kind of joint do we select? So, well, let's guarantee the stability of the structure by the equilibrium of it, logically. But also, if you have the freedom of choosing well, there are other parameters like, the effects on other parts of the structure, but you know that if you work with fixed ends, let's say columns, it's going to be prone to resist more creeping load or more axial load than the others because of the variation of the physics of the what it's called of the effective length based on the type of joint. That's something now. So you're getting that whenever you're designing a column or certain column, the ends matter. It's not just that you cut, you just release the column from the ends, from the beams, roof, from the floor, and as well, let me work now. Ends matter a lot. These are nice charts I did. So when you use Euler's formula to calculate the crippling load, and then you say, well, instead of the crippling load, I would like to have the crippling stress. So I can say, well, the crippling stress is a force divided by the area. And I know that the moment of inertia can be defined in terms of the area and the radius of gyration, as said before. That formula was before, kind of, we already saw it. Then, and I do some magic here, kind of put my things here, see? I end up with this formula here. A formula that says that the stress, the crippling stress depends on the slenderness of the square of this, on the slenderness of the column. And if I plot that for example, any column, you're going to see that Euler's, this formula here, what produces is this curve here. Yeah. That says that if you didn't have anything else what I drawn there, that if you have a column with a very small slenderness, what's going to happen is that this is going to be asymptotically approaching the vertical axis. Asymptotically means that it's going to approach the vertical axis, but it's never going to touch it. So it's going to run to the infinite, but it's never going to touch the vertical axis. So it's going to be asymptotically approaching that vertical axis. So which means if you have a column with a very small slenderness, then this is, so would it mean that it can withhold millions of kilonewtons? No, it's not like that. So there was a flaw in Euler's consideration. Well, not a flaw, there was a limitation on in which type of columns using Euler. So because if I have a material with that strength of 330 megapascals and I plot it here, so whenever it cuts here, I say, well, columns with slenderness value that fall into this region, they're going to fail not by what Euler says, but by buckling. Remember that in steel structure, well, in steel, depending on the slenderness, there is a type of failure associated to that column, crushing plus blocking, buckling, and then buckling. Then it happens to be that most of the time this is 80. And still, medium columns are here, where it says, well, medium columns can fail either by crushing or by buckling. But you see that Euler is not the best to tell you that. It's true until this point, that's it. But then, on this point, perfect. No, let's use it. So Euler had a limitation here. And then I'm going to show you that two more things, or two more approaches that came after this. But you see that this is not when you start looking at the formulas from this point of view, you say, well, yeah, that's true. This doesn't work all the way around, as it says, doesn't work. Works. Actually says that Euler is fine, to work with these long columns, over 120 of slenderness. And you're sure you could use Euler here, from the theoretical point of view. We have an exercise. Let's talk about the other methods and jump to the exercise. Yeah. So another two methods that appear were these two. Rankin's formulation and Johnson's parabolic formula. There are other methods, but these are, the physics behind column design, this thing. Rankins was, and I'm going to put it in a very simplistic word. Rankin said, so you mean that a column might fail by either crushing or buckling? So what about if we, here the word, superimpose those effects and give it like that and treat it like that? That's it. And you see, he said, hey, the crippling load depends on what? On the crushing load and the Euler's load. This is buckling, this is crushing. When you see this formula, I don't know if you notice the composition of the formula, but when I first saw this formula, I said, now I see it. If you study a little bit of electrical engineering or electricity, and you're working with resistors. So resistors in electrical engineering, or in electricity, is something represented like this. No? It's like this, and then you can have, well, this is a power source, voltage, this is positive, this is negative, and this is the resistor. Yeah. Then when you want to calculate, for example, okay, how much is the current flowing through the resistor? So, well, we can use Ohm's law, this one here, to calculate the current current resistor. And you say, well, the current, what was the word, is R V divided by R or something like that. Actually, I should remember Ohm's law. Yeah, this is I. Yeah. You say, wow, beautiful. You have a voltage, 24 volts, 120 volts, 220 volts. If it's all the type of current, alternate current, well, it's a different thing. But then you have a resistor, and then you have the current. But somebody came and said, yeah, but you know what? I would like to have another resistor in here. What do you call another resistor? Yeah, I want to have another resistor right next to it. And I want you to tell me, now what's the current? Wait for me. This is not electrical engineering for you, but it's kind of something that is related. So what's the current now? Well, when we have two resistors, some people start, working their mathematics and stuff. Well, the total resistance of this is going to be equal to the sum of the individual resistance. Then it means that then the current flowing there is going to be the voltage times the total resistance. That's beautiful. Came another person and said, yeah, but I don't want to have it like this. What do you mean? Yeah, I want to have it like this. Delete this. I want just to, put it like this. Tell me now what's the total current flowing through that system, to that thing. And they complicated things and stuff, and somebody came up and said, well, if you want to know the current going through that system, you need to calculate exactly. You need to calculate the total resistance and look at this formula here. Samaya, you are flying. Thank you. Yeah. Look at this. What can I tell you? The considerations in these circuits, parallel circuits are called this, is how to measure the contribution of each resistance to the total resistance. Rankin's case is more or less following how to measure the contribution of each failure mode to the critical load you could impose there. You see how beautiful is this? Rankins uses some constants depending on the material stuff. So this is not the final formula. The final formula is a nice rearrangement. Actually, the final formula for Rankin's formulation is related to the crippling stress, or the critical stress. Yeah. But when you see this, so he was trying to weight the contribution of each failure mode with this. I don't know if it's if coming from the electrical point of let's say field or not, but the similitudes are astonishing, not stunning, astonishing. Nice. Yeah, here are the definitions of those. If I plot rankings, this is my plot, by the way. This is I did it. If I used Python to plot it. So if you plot rankings, let's say curve, you're going to have here, this is Euler, and this is ranking. Yeah. You see how smooth it goes? And And this is the 330 mark we use, megapascals. So this is the kind of a reference material. It's not, you know, so we can say, okay, that Euler starts working here, but Rankins, might seem that it works all the way down. But one thing that happened was that when they were testing columns, failures were happening in this region in between. So they said, well, Euler kind of overestimates the amount of load. Rankin kind of underestimates the load. So if I underestimate, it means that I'm kind of wasting material because I'm using a geometry that is enough for more. But if I use Euler, it means that with less load, the column might fail. What should we do? And there comes Johnson. So, well, we can use something called Johnson's parabolic formula. Has that shape, and it's this green one. Look at this, nicely. And it touches this point. This point is known as the, man, I had it, but I just missed it. It's coming. This point is coming kind of, I believe, is the critical slenderness of the column. So it's a point where Johnson and Euler are tangent, touch each other. And what people said, we are simplistic. Said, well, you know what? You work with, calculate the critical slenderness. If your column is less, your column's slenderness is smaller than the critical slenderness, use Johnson. If your column slenderness is larger than the critical slenderness, use Euler. So you could imagine that. Any questions? Sometimes the history of these developments is even more interesting than the development itself. Wow. And yeah, let's go up before jumping to the exercise. So eccentric loading. What does it mean, eccentric loading? That if I look at the column from the top, I'm supposed to apply the axial force here. Use another color like this one here. This is supposed to be this application of the axial load, but it could be here, it could be here, it could be here, depending on the flaws in the construction process. So somebody came up, I don't recall the name or the group, with the second formula. I don't know if I'm not pronouncing it correctly. Second formula, and the second formula is very similar to to Rankins. Put it here, because what I want to show you, I'm not interested in you. Well, you can know the equation and everything, but what I'm interested is in the core concept of this. That the second formula, which I don't know, well, this is P divided by A here. I don't know why it depends on the maximum stress, and one term here, which is called the, I believe it's eccentricity ratio. Yeah, eccentricity ratio. And when I plot the curve related to the second formula, which is here in green dotted lines, in this one here, here. So the varying the eccentricity coefficient, I think it's called. Why I forgot that. Eccentricity coefficient. The capacity of resistance of your column is reduced. Yeah. So meaning that the farther away you put the force or locate the force with respect to the central axis of the member, the less capacity to support that load the column is going to have. What I mentioned at the beginning, that even smaller loads can create failure, can produce failure in the columns. But the thing is that there is a small region. So this would mean that I have to be very accurate with the location of the force. So imagine a monster building, and you measure to the millimeter the positioning of the axial force on a column. It's crazy. So what people figured out is that, yeah, but depending on this coefficient of eccentricity, there's a rhomboid area where you can put the force, even if it's a little bit away from the central axis of the geometry of the member, and the variation is not going to be that much. So that was on the, so it's not that I have to be accurate to the millimeter. No, 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 no. Or precise, yeah, precise to the millimeter. No, 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 no. You can be a little bit off. And even though if you're a little bit away, you could, forgive yourself to tell, I cannot put this in the centroidal axis. I'm going to put it a little bit away. So how much force would be? And this is where, for example, if you take an IP 120, a beam profile, and you say, you know what, I cannot locate the force or put the force here in the center. I'm going to put it like here. Then you can calculate, for example, how much is that. So meaning that even though your assembly process is not perfect, you could estimate or use safety against that. And that's the reason for these considerations, because you're not going to escape from using eccentric loading. So if you're not going to escape, okay, let's quantify the magnitude of things. Yeah. So in this case, for this example, the process was that I wanted to know for which value of the coefficient of eccentricity of 0.2 would be for me to put the load where, far from the central axis. Then if I use 0.2 as coefficient of eccentricity, then it would mean, or that would be equivalent to putting the force about 20 millimeters apart from the center of the beam, the web of the beam, of the column. And then that would be equivalent to using this line here. This line here. So the capacity was reduced. This is the type of conversations you have. All right. But one interesting exercise we're going to do here about the physics, as I mentioned, in your next subjects, kind of in design of street structures, concrete structures, and so on. There is more affinity, but this is the physics behind everything. Euler is used as a base for the Eurocodes, but it's not the standard. This is purely academic and theoretical. Yeah, this is not standards. What they use is more relevant, up-to-date information about material under testing procedures, and then they produce a nice set of let's say factors to use for that. So I believe in this exercise one that we're going to check out now, what I'm going to do is I'm going to solve this by using Euler, the typical method, but then I will try to solve it on a lighter version of what Eurocode 3 is the one related to design steel structures, would do. And you're going to see the difference, and we're going to see how different the estimation of the critical load is going to be. Simple column. It says, I'm going to mix a few things here, but it says something like this. Define the safe load of a column with the following characteristics. So both ends are pinned. So we remember that if both ends are pinned, the physical length is going to be equal to the effective length, or the effective length is going to be equal to the physical length, because I can actually come here and bring the table. Where are you? Here you are. I hope I can take it here. Yeah, I could. And I'm going to put this into this one. Yeah. So I got distracted by this. So then we have the physical length of the column, L lowercase, moment of inertia around the x-axis. Take it like this. And we're going to see something beautiful related to the moment of inertia. Moment of inertia with respect to the y-axis, area of the section, the safety of factor that they're telling me to use, but that's from the problem, and the modulus of elasticity. And here we have Euler's formula. Yeah. So meaning that if I wanted to use this, of course, the first thing I'm going to use is that, okay, what's the effective length of the column? The effective length of the column you need to use is pin. Pin is this one. So I mentioned, the effective length of the column is going to be equal to the physical length of the column, which means that if I write here, length is going to be L, and it's going to be equal to this L, 6 meters. So no changes there. Then what it seems is that I just need to use what is called the L. Just the L, yeah? That's it, no more than that. But I could just be ahead and try to calculate things. So I can say, well, I just need the L, I just need the modulus of elasticity, I just need the inertia. So if I want to calculate the Euler's critical load, I can do it right away. Yeah? Euler. Here we are. I can do it right here. Now, the formula tells me you need to use, again, it's not working. Hi, guys, sorry about this. Why I frame document. Sorry about this. Frame document. Frame document. I hope I don't mess things up. Yeah. So the question, Euler's telling me, okay, what's the moment of inertia of the section? Now, this section has two moments of inertia depending on how I look at. So what do you think it should be the moment of inertia I should use? The larger one or the smaller one? Because it would make a huge difference, isn't it? Again, as I mentioned, as an engineer, we need to look at the formulas because the formulas are going to tell us a lot without doing any calculation. If I use the largest moment of inertia, the moment of inertia is in the numerator, meaning that the larger it is, the larger this becomes. And the smaller this is, the smaller this becomes. Means it makes sense that if I want to calculate what, if that's going to fail, around which axis is going to fail. Is it going to fail around the x-axis, or is it going to fail about the y-axis? When I see fail, it's kind of buckle, around the y-axis or around the y-axis. Well, the smallest axis, the smallest moment of inertia is going to give you the smallest critical load, which means that if I would use this largest moment of inertia for calculation, then it might buckle around the y-axis. So you always have to use, talking about Euler, the minimum or the smallest moment of inertia. So that is, if I want to calculate the critical load according to Euler, is going to be equal to pi, let's write as pi, time pi square times E, which is this friend here, times the smaller moment of inertia, this one here, and I divide this by the effective length of the column. There it is. Sorry. Yeah, it should give me that. Column square, length square. I was checking at the units, kind of something wrong there. Here it is. So I can put it nicely, say, well, let's put some highlight there. So we have it. So according to Euler, don't put more than 250 kilonewtons. If you put more, so you're going to have buckling failure. But now, we didn't talk about the slenderness and anything. And we remember that Euler doesn't work well with certain values of slenderness. So meaning that if I calculate the slenderness ratio of this, and this gives me a very small slenderness, means that Euler is not the right thing to go. Yeah. So let's calculate the kind of the slenderness of this. And we know that to calculate the slenderness, we need to there's a relation, and let's call it here slenderness. Just to verify things. Actually, when you do this process using Euler or Rankins or Johnson's, the first thing you do, even though it's not asked, is calculate the slenderness to see where it fits, how it should fail. Yeah. So if we come here and say, hey guys, slenderness, I know that is defined, yeah, by the relation that exists between, where are you, lambda here? Between the, what is it? The length of the column and the radius of gyration. Yeah? And we also know that the radius of gyration, k, is a relation that exists between the moment of inertia and the area. So it's going to be square inertia divided by area. That's the formula we've given before. Yeah. Uppercase. Oh, there it is. Meaning that I can calculate A by saying, okay, first the radius of gyration, okay, is K equals to square root of the moment of inertia, which is the smallest one, divided by the area, which is this one. There it is, 2.87 centimeters. So that would be the fictitious mass particle away from the center of the Cartesian coordinate system, to represent the mass distribution of everything there. Then I'm going to have that the slenderness is going to be just, calculate L divided by the 210, which means in this case, a slenderness let's leave things like no. A slenderness of 210 means that this friend will fall in this region, and it can be considered such as like a long column, like in this region here. And if it is a long column, then Euler is magnific to calculate the creeping load of that column. Beautiful. And again, when you do this, it's the other way around. So you first calculate the slenderness to see where you are at, and then calculate the appropriate formula. Right? Now, but what happens if I compare with a light version of what the standard says? Basically, Eurocode code 3. So we're going to have there. So one of the things we need to check out is that we need to have certain assumption. Yeah. And for Eurocode, in general, there are tons of factors you need to use. Yeah. So let's create a table of assumptions. And then let's put it nicely bold here. So, well, the first thing we're going to do that it was not mentioned there is that we're going to use, like, who was it? It was Jude Sagar mentioned about the A36 and the S standard. So yeah, I believe it was you. Very nice question. So let's assume that we're using, a steel grade of, this S275. And then for that steel grade, we're going to have a yield strength associated with that steel. And that yield strength, we're going to call it Fy, and that's going to be equal to 275, as the megapascals. And we're going to say that, well, that's hot roll I-beam. Beautiful, yeah? Or I-section. Let's not call it beam, I-section. Then let's say, okay, we're going to have an elastic modulus, E. Now, I'm going to use this like this to differentiate it from the one before we used, so it doesn't create some conflicts in the software. And we're going to call it 210 gigapascals, or we can use the same, the same 200 just for comparison process. Then the length is going to be the same, but the effective length, we're going to give it a different name just to keep track of things. Effective length, I'm going to fly here. I'm going to call it, kind of this L critic. And that's going to be equal to this L that we have here. And then the area of the section is going to be the same. But now Eurocode, they don't just freely give or easily give you, use a safety factor of 3, like in this case. No? Well, this is not the safe law, because the safe law of this would be exactly this divided by n. So it would be this much. So this is not the case. But he said, well, there's a safety factor you should use, but it's called partial safety factor. And that's what's the letter for that? Is psi. Gamma. No, it's gamma. I believe it's the word for that. Yeah. Is it? Where are you? Oh boy, I missed it. Where are you? This one, gamma. Yeah, gamma. And then it's going to be M1, and that's going to be, look at this. So the safety factors in your code are either 1 or 1.2, 1.1, depending on the national annexes that are used. Anyway, so the first thing we're going to do is to use calculate the calculation of it's called non-dimensional slenderness. And that's a slenderness that depends on the strength of the material, thing that doesn't have Euler. So we're looking at differences now. So for that, we need to calculate what is the they call it like this: the x radius of gyration, which is going to be then this divided by the area that it is. Let's put it in millimeters just to be starting working fully compliant. And then you have the y radius of gyration, and that's going to be the relation between, obviously, this friend and this friend here. And again, John put it in millimeters. There it is. Then the slenderness ratio, it's going to be, now I'm going to call it like this: lambda, both slenderness ratio, because it depends on both sides. Xx equal to then the critical length and the radius of gyration, this one here. And then if we do the same with the other one, with the y-axis equation, lambda, where are you, lambda? Here. Then it's equals to the length divided by this radius of gyration. There it is. Now, we can calculate the non-dimensional slenderness ratio. And again, we're going to have it in both cases. The non-dimensional slenderness ratio is kind of, let's write it down. It's going to be lambda, and I'm going to call it like this: non-dimensional xx, and that's going to be pi, this friend here divided by pi. I don't know, this is beautiful, the process on how they come up with these formulas. Times square of the strength of the material divided by the modulus of elasticity. This is the non-dimensional slenderness ratio, it's called. And then for y, oh my goodness, I need to use this one. And then in this case, what you do is you don't use the smallest one, you use the largest one, the non-dimensional, and then you compare it to basically one to say that, to calculate something called the buckling reduction factor. I will give the full example, reduction factor. And then this buckling reduction factor, you look at how stepwise the use of standard comes. Is defined by this equation. The letter name is psi chi. This one. And then that's going to be equal, depending on the variation, it's going to be equal to 1 divided by the largest one to the power 2. There it is. And my friends, what's now? Buckling resistance. We're coming to an end. And the nomenclature for this is NB. Don't ask me why. It's going to be what? The multiplication of the buckling reduction factor times the area, where are you, area of the part, which is this same one, times the area. I don't know why. Yeah, times the strength of the material, boom, boom, boom. And that's going to be divided by who? By the safety factor. And our safety factor is going to be this one here. And John, you have an error there. There it is. Just a little bit cosmetic changes. There it is. And I can just put it also highlighted. And let me bring Newton's, I called it P, was? Yeah. Sorry, Euler. Conclusion. So even though there are many things going on in the standard, which is the one we should follow, you see the difference? I mean, it's not a huge difference, but might be for this case. But Euler is kind of the basics behind, the physics behind column design. Standards are a super improved version where committees, teams, university have done a lot of tests to validate each one of these factors, formulas, and everything. Whew. And that's it, my friends. Key points. You might not remember what the formula for a column is, but you should remember that how you connect the column to the ends matter. I have a question I'm going to answer soon. And then size of the length and geometry matters, and then that's all. It says, Sagar, if I'm designing practical columns, do I have to always check buckling in both axes, or I just check the weaker one only? Typically, you go through depending on what is the premise. For example, here, we needed to, no, you just calculate, so you just check the weaker one. But the definition of a weaker one might not be that the one that is smaller. Let me explain you why. In Euler, yes, the weaker one is the one with, with what you call it, with less, what was it, less moment of inertia. Yeah, definitely in Euler is that, but practically, you're asking, you need to use the larger non-dimensional slenderness ratio, which would make sense at some point to, that is not correlated to the weaker axis, basically. You see, the standard what it says is that you need to compare the largest non-dimensional slenderness ratio with a value to know on how to calculate the buckling reduction factor. The buckling reduction factor considers kind of material flaws, deformities, and crookedness and stuff, kind of a bunch of imperfections in the column. Yeah. So by defining what is a weaker axis is a little bit complicated in the sense that you need to get the results first to know around what you should be considering this. Well, it's a kind of a mouthful, but you see the difference that happened between Euler and this one. Yeah. But definitely in the end, as physics provide, columns are always going to fail around the weaker axis. But in calculation, might think a little bit different because we're using this is a weaker axis, but we're not using this as a consideration because we're using this because it's related to the geometry, the geometrical difference between the two inertias. I said a lot of things, but I don't know if I answered your question. But I think I did. But the thing is, guys, is that there's a step-by-step procedure on this. So it's kind of non-thinkable in the sense you just follow first part, second part, third part, fourth part. Yeah. But the difference are not that much. Sagar, did I get to answer your question or was too much? Good. Well, guys, thank you for being here. See you next week, I think on Monday, face to face. And thank you and have a beautiful weekend coming soon. Take care. I'm going to upload also this recording to Moodle.